Good morning, everyone from the East Coast of the United States. If you're further east of me, it's your afternoon or evening, I guess, but thanks for joining us. We'll be talking about a library called dtype-next. I'll go ahead and share my screen here. Before we jump into the presentation itself, I just wanted to make it clear to anyone who's new to the project that dtype-next is part of a larger set of work called Cyclos, which is aiming to develop some libraries and tools to facilitate data science and machine learning. This is the main website at cyclos.github.io, and I encourage you to take a look at this. We will be looking at dtype.next, which falls under this array programming category, and we'll briefly touch on a couple of related libraries that allow us to work with data sets or sort of tabular sets of data that those higher level libraries are built on top of dtype-next, as we'll see, particularly TechML data sets and the tablecloth. All right. So please explore the Cyclos website and get a better idea of how this all fits in. First of all, I'd like to thank my collaborator, Ethan Miller. He's created the framework for this workshop. So let's get started here. Ethan has created a template on his GitHub page. We'll post this link in the Zulip chat. You can visit this and basically clone this repository, which includes both the code samples that we'll be looking at today, as well as a sort of empty project that has the boilerplate you'll need to pull in the libraries that we're going to be working with here. Also, we'll touch on this a little bit later too. Ethan has some suggested follow-ups. If you're interested in what we covered today, you can try some of it out. There's a couple of simple things here, but he also has a link to a set of exercises that are geared towards NumPy, which is a Python library, which does some of the things we're talking about today. But a lot of these exercises are easily applicable to dtype-next. So this would be a good follow-up exercise to work with some of the stuff we're going to cover today. So let's look at the goals of the workshop. Primarily, of course, we're going to take a look at what dtype-next is and get a little idea of how it fits in with the larger Cyclos ecosystem. We'll talk about why dtype-next is useful, and look at some of the key concepts that you'll need to understand in order to effectively work with the library. We will be working on, generally speaking, potentially multiple dimensional arrays, but dtype-next has its own particular way of looking at those, and we'll work through some simple examples. But to be clear, this is an introductory workshop, so we're not going to get too heavy into focusing on realistic data sets or particularly large sets, but we have a couple interesting things towards the end that we'll work on. So what is dtype-next? This is a library created by Chris Nernberger. Chris is a prolific tool creator. We can look at his description here. dtype-next is intended to provide a unified pathway for dealing with contiguous containers of mostly primitive data types. It allows us to avoid boxing of these primitive types into larger reference types, which often has a pretty substantial performance penalty in the Java world. dtype-next also provides some facilities for array programming. If anyone's familiar with APL, you can treat arrays as though they were primitive types and do a scalar multiplication or array addition without having to worry about all the explicit loop iteration over various dimensions that you might normally have to do. There are some additional ongoing goals of the project. A lot of tools have already been written in the Python world, and part of the point of dtype-next is allowing efficient interface to particularly non-Java C-based systems. And one of the things that's currently being worked on, I guess in Java 16, there's a new foreign function interface that dtype-next is helping to support that. This GitHub repo has a handful of useful links to some other documentation. This is a sort of typical Clojure sort of API, the various namespaces broken out here. And this overview has some additional examples to explore. Hopefully what we covered today will make these comprehensible. And I wanted to quickly draw attention to one of Chris's notes here about why dtype-next. The next in the name here refers to the fact that Chris has already solved a lot of the performance problems, I believe, that he was trying to tackle in his earlier, I guess it's called dtype. The current work also involves improving performance in other areas aside from just runtime, in terms of compile time and startup time, pulling all these dependencies into the Clojure JVM. So we'll see in the code that there are references to effectively the version 3 of this library. You can see that here, I guess. So that's specifically what we're going to look at is v3, which is the dtype-next. So just to sort of summarize here, here's in Ethan's words, dtype-next provides a typing system. That's one of the ways that we can improve our efficiency here. Often in Lisp or Clojure, we don't focus too much on the types of things that we're working on, but that can lead to some inefficient performance. And dtype-next also provides some abstractions. The chief among them being what we'll see as a concept called a buffer, which is an abstraction for an array of data, but it doesn't necessarily represent a concrete chunk of memory. We'll see that it's a little bit more flexible and more abstract than that. And finally, in our summary here, we can see that, as I pointed out, a number of these other Cyclos systems are built on top of dtype-next. Dtype-next is a relatively low-level library. A lot of focus on the interface between Java and Clojure. Built on top of that is this TechML dataset library. If any of you are familiar with working with some of the Python data science libraries, dtype-next is somewhat analogous to NumPy or R vectors if you've used the R programming system, whereas TechML dataset is more like pandas in Python. And then even further up, we have another library called tablecloth, which provides a useful, consistent interface to working with tabular data. So we'll play a little bit with TechML dataset later on in the workshop. But let's jump in now with some actual code examples. I'm going to be working here in Emacs with Cider. Get that started up here. So the fundamental namespace that we're going to be looking at today is, again, the v3, which is the next part of dtype-next, is this Datatype namespace. Conventionally, alias is dtype, but we're also going to spend some time looking at an auxiliary namespace called functional, which provides a lot of useful features to work with the dtype structures. So go ahead and load both of those. And let's start by considering the question, well, why bother with dtype-next? Why not just use built-in Clojure sequence types? Well, the short answer, of course, is performance. And so here we'll run a quick little benchmark, this criterion benchmark framework. We'll take a standard Clojure sequence of 1 million elements and use reduce to sum them pairwise. And this benchmark is going to run through several cycles of the evaluation. So it takes a moment here. So let me get my screen adjusted here. So again, this benchmark is executing that code multiple times. And we can see here that the mean execution for that summation of the 1 million elements is about 6.7 milliseconds. Now, if we perform the analogous operation using dtype, we'll see that we're going to create a structure called a reader. We'll see in a moment that the reader is one of the two types of buffers, which are the core idea here. And it's clear that we're giving it some explicit type information here with the signed 64-bit integers. And notice that rather than using built-in Clojure reduce and plus functions, we're going to use this sum function from this functional namespace, which is designed to efficiently manipulate a buffer. So when we execute this in the benchmark, we can see that the average execution time there is only 1.5 milliseconds. So we're looking at, between 1/4 and 1/5 of the time that it takes with the raw Clojure types. So that's, of course, our chief argument for what motivates dtype-next in the first place. So let's look at this concept of the buffer that I've mentioned a couple times here. A buffer is an abstraction. It's really simply a Java interface that provides efficient random access. It's countable, and the elements, the type of the elements are known to the buffer. And it also has an interesting pair of properties that it's lazy and non-caching. We'll see that in action in a moment, but essentially that means that the buffer is not necessarily committed to the memory or the computation required to realize the physical representation of this sequence of data. We can, in many cases, defer forcing a concrete realization of the structure until we actually need it. So when we chain together a number of operations, this can be very useful and very efficient, that we don't necessarily have to make copies of 1 million elements at each stage of the chain of operations that we're performing. We'll see some examples of that in a moment. Let's take a look at an actual buffer here. We can construct a buffer out of a basic Clojure persistent vector, and this may or may not be surprising that when it's printed out, it still looks like a vector. And in some ways, it also behaves like a vector. And I believe that this is intentional. That's where the details are not important. We don't have to worry about them. So we can take this buffer and we can use some of the built-in Clojure functions, because it does implement these interfaces. Sorry, I forgot I was going to quickly take a look at that. Here's the actual code for the buffer in GitHub, and as you can see, it's simply a Java interface, and it implements random access, sequential. I'm not sure exactly which one of these interfaces guarantees that it's countable, but because because it implements those interfaces, it works fine with these built-in Clojure functions. So we can efficiently grab a random element from the buffer, or we can count it. However, despite the superficial similarity to a vector, it clearly is a different kind of thing. That may or may not be surprising to see this reify on the end of that. Does anyone understand that, or is that surprising? Anyone explain what's going on here, maybe? The short answer is that this class of this buffer is sort of an anonymous class that simply implements a Clojure protocol. So this information is not particularly useful for us looking at this class directly. So instead of that, normally what we do is use one of the functions that dtype provides called Datatype, which allows us to get a little bit more meaningful information. So when we apply that to a standard Clojure persistent vector, we get the expected response there. And then when we apply it to a buffer, rather than using class here, we get a more useful answer. Furthermore, we can look inside of the structure and look at the data types of its elements here. And this may be a little bit surprising too. It looked like we were creating a vector of numbers, turning that into a buffer, but dtype considers those to be objects. Does anyone, can anyone explain why we're getting this result here? As I mentioned earlier, we're primarily focusing on primitive types, so we don't have to worry about boxing. The simple answer is that we didn't give dtype any type information here. So in this this Clojure vector, what appear to be simply integer values are actually turned into Java long objects, and that's what dtype is seeing when we create this buffer. So in the absence of any more detailed type information, it simply has to see them as objects. So of course we can be a little bit more precise and say, for instance, we're going to create an int array. Then dtype will recognize that those are 32-bit signed integers. Another alternative is to use this vector of function, and again, this is a little bit of a glitch in dtype, that this vector itself has integers, but by the time it's constructed into a buffer, we lose that type information. So this is one of the areas where you have to be a bit careful, sort of moving into and out of normal Clojure into the dtype world. This case here is a little bit easier to understand. So another that we've been using this as buffer function here to convert Clojure types into dtype types. Another way to do that is to directly create a reader. Again, a reader is one of the two main types. The other is a writer, which we'll look at in just a moment here. When we use this reader function and give it the specific type information, again, it appears superficially to print like a vector, but we preserve the primitive type information here. And finally, we can look at the full range of primitive and other types that the dtype-next supports. All the expected signed and unsigned integers, single and double precision floats, as well as a generic object for other types of things, strings or more complex types. So we've sort of informally looked at the readers here. Let's look at that a little more closely. The reader and writer are the two main subtypes of buffer. As you might expect, a reader is an immutable structure, which is probably something that most Clojure programmers are comfortable with. As we saw with the buffer interface, there are a number of read and write functions that are potentially implemented. However, for the reader, the write operations are not supported. So if we try to change an element of the reader with this set value function, which has the typical bang character, the exclamation mark at the end to indicate that it does cause a side effect. We can see that doesn't work. It's an unsupported operation. The readers simply don't implement the write methods of this buffer interface. On the other hand, if we have a writer, that works just fine. We can change the index 1 element to 0. So in many cases, we're content to work with a reader. In cases where you really do need to be able to update an existing structure, the writer would be more appropriate there. I mentioned before one of the kind of surprising characteristics of a buffer is that it doesn't necessarily commit you to, again, either the physical memory or the computation cost of realizing the entire structure up front. So let's take a look at a clear example of that. There's a macro called make reader, which you give it type information and a number of elements. And this is a somewhat unusual kind of macro. It's called an anaphoric macro, which may be unfamiliar to some of you. An anaphoric macro refers to the grammatical idea of anaphora, which is a word, typically, I guess, a pronoun that only has meaning in a given context. A simple example would be if I ask my wife, "Have you seen my wallet?" And she responds with, "It's on the table." So the word "it" doesn't really mean anything independently of that conversation, but in that context, it refers to the previously identified object, the wallet. In this case, this IDX symbol is the anaphora, and it refers to naturally the index of each element in this structure that we're building here. So it has a sort of surprisingly in other words, you kind of have to know that IDX is meaningful to this macro. It's not an arbitrary symbol. You have to kind of be aware of that ahead of time, which is one of the confusing things about anaphoric macros. They can be very concise, but you kind of have to know a little bit about the inner workings. What we're going to do here is, in a way, kind of silly. We're going to just fill this buffer up with some random numbers. The product of the index 0, 1, 2, 3 on with a random integer. But we'll see some interesting behavior here. So we'll create the reader, and we'll go ahead and examine the first 5 elements. What's surprising here, though, is that despite appearances, this reader structure is not an array of 1 million elements in memory now. It is sort of a potential array. And we can see that if I reevaluate this same expression here, I get a different set of numbers. Each time I evaluate it, it's likely to be different, because this is not a concrete contiguous chunk of 1 million elements that has been already computed. What this is saying is that when it is required to produce a value, it will use this expression here based on the index to determine that element. And so when we take the first 5 elements, it forces it to do so, but it's still not committed to that as a concrete representation, so that each time I evaluate this, it gives me a new interpretation of this. And another way of looking at that is if we take 5 elements close to the end of that abstract structure, they're produced just as quickly as the first 5. So we don't have to compute all 999,000 and then the 5 I want. We can immediately get them, because this is sort of an abstract entity. It's not the actual physical thing in memory. However, at some point, we may need to work with an actual concrete representation of that. So we can use this container function to turn the buffer into a physical actual representation of memory. So now we are turning this into 1,000,000 elements of an array. And we can see here that each time we evaluate this, it is fixed. So we forced it to a concrete representation now. So just keep that in mind, that the buffers are not only lazy, it doesn't do this work until it's needed, that they're also non-caching, so that and that's perhaps only really evident in a case like this where we have some random values. But this makes buffers more efficient to work with. It also makes them a little bit more surprising to work with. So let's look at some.
David,
Yes?
is it okay to ask a question?
Please.
Yeah. So about this non-caching term, I'm trying to compare this to what we're used to, which is a lazy sequence in Clojure.
Mm-hmm.
So in a Clojure lazy sequence, once we realize it, it is already there, right? And that is why we needed to say here, no, it is non-caching. Once we realize it, it is not there. We will need to realize again. Is it correct? Or maybe I.
Yes, and again, I think perhaps that's only really visible when you're dealing with some sort of randomness. That if it's deterministic, you might need to realize it each time you evaluate this here, but it wouldn't be visible, right? That you get the same result each time. So,
but it might be slow.
You're right. It could be if you maybe this one here, it would require you to compute 900,000 of them first. So yeah, I mean, both in terms of memory consumption and computation, this would require more work, right?
Yeah, thank you. I see. Thanks.
Okay, thanks, Daniel. Again, if anyone else has questions at any point, please feel free. So as we saw, in some cases, we can continue to use built-in Clojure functions to manipulate dtype objects. Here, we can use Clojure's reduce and plus operators to sum up 1,000,000 integers, and that works just fine. Here's another case where we can say filter out ones that don't meet a certain criterion, or we can simply count the number of elements. The downside, however, is that often using these built-in Clojure functions takes us out of dtype world and back into the world of regular Clojure. So, for instance, if we see here, this is very simple and convenient to call keep on this, but when we look at the type of it, we see that we wind up with a Clojure lazy seek, which is not the buffer that we started with. So much of the time, rather than using these built-in Clojure functions, we prefer to use these operators in the functional namespace that I mentioned earlier. These are designed essentially to take buffers as inputs and produce buffers as output. So, for example, if we define a couple of buffers to play with here, each with 4 elements, we see that the subtraction operator in the functional namespace can simply operate on these 2 as though they were simple scalar values. So it handles the pairwise subtraction of elements, which is very, very convenient, but also at the same time keeps us in the land of data type or dtype-next, with a buffer being the result, rather than, again, what looks like maybe a Clojure vector is actually still a dtype buffer. For convenience, many of these functions are overloaded, so we can do a scalar subtraction. Simply subtract 2 from each element of the A buffer, or in probably a less likely case, we can simply do the difference of 2 numbers. So these operators in the functional namespace give us a lot of flexibility here. Another couple of simple examples: we could take the A buffer and square each of its elements, or take the logarithm of each of its elements. Again, no explicit iterating over the dimensions of the array. And while each buffer has its own type information, the functions in the functional namespace will handle casting as necessary. So if we create one buffer of signed 32-bit integers and one of single precision floats, we can see that each of those buffers carries the expected type information for its elements. But when we do a matrix multiplication here, I think this is probably the expected result for most people, that rather than trying to convert the float to an int, we have to promote the integer to a float. Otherwise, we lose the fractional parts of our numbers here. What's a little surprising maybe, however, is that it's actually been promoted to double precisions, even though our inputs were singles here. So as with Java, apparently double precision floats are sort of the more natural default value to use. We saw earlier up here that not only could we use a basic Clojure addition operator, we can also use reduce, but that again winds up taking us out of the dtype world. So dtype provides some alternatives. For instance, here, instead of Clojure map, we'll use an operator called emap, which takes a buffer and maps some arbitrary function over that buffer to yield a new buffer. This one is possibly a way to maybe initialize a buffer of all 0 elements. It it maps this constant function, which always returns 0 over this range here. This one's maybe a little more interesting. We'll take a range of floats and essentially add 10% to each of them. And there are other operations that are built in. We can take a slice of a buffer, subsequence of that. And one other area that's interesting to explore here is that a lot of the efficiency of the buffers comes down to how they manage the indices of the elements. Here we'll take a look at how to extract the indices directly. For an example, let's consider taking this range of integers and applying this predicate odd to determine whether each element is true or false. But instead of these logical Boolean values, what if we wanted the actual values themselves? We could use Clojure's built-in filter function, but again, that takes us back into the world of Clojure data types. Another alternative is in this argops namespace. There's an alternative called argfilter. So we can see here the output of this is a dtype data structure. And to be clear, that these are not the elements that satisfy that odd predicate. These are actually the indices of those elements, which is kind of a little confusing here because they turn out to be the same thing. The element 1 is the number 1, element 3 is the number 3, and so on. But those are the indices, and we can see that more clearly here if we break this apart. The arg filter will extract the indices from this reader buffer, and this function indexed buffer allows us to apply those indices to the reader to extract the elements identified by those indices. Again, sorry, this is maybe not the best example because again, the index and the value correspond to each other here. But these are the actual elements versus the indexes of those elements here. All right. We are not quite at the hour mark here, but we're about to tackle a little bit more extensive exercise here. Should we take a quick break, you think, Daniel? Or
yeah, wonderful. Yeah, perfect timing. Yeah, what do you think? 5 minutes or maybe 10 minutes? What would be good?
Sure. Maybe 10 minutes. Before that, does anyone have any questions or anything you'd like me to cover a little bit more thoroughly? Or Okay, so let's go ahead and take a 10-minute break, stretch your legs, get some coffee. We'll see you back in a bit. All right, welcome back from the break. We just had a question raised here in this last example we're looking at. We have a predicate called odd question mark here in the functional namespace. And there's another similar looking one here. This, of course, turns out to be the built-in Clojure odd predicate. And the question involved, why one versus the other. Turns out that in this case, the version in the functional namespace knows how to apply itself across a buffer. So obviously that's why we don't use the built-in odd here. The question is, why not use that functional odd here? I guess the simple answer is the intended input. So this, in the functional namespace, this odd predicate takes a buffer as an argument, and it knows how to process all the elements individually there. Whereas this one, we've kind of turned that inside out. We have a function that only knows how to handle a single number, and then we're using a higher order function called argfilter to do the element-wise application of it. And I think the more profound answer to your question, Yanni, is that this illustrates that while there are many useful pre-provided functions in the functional namespace, there will be functions that you desire that aren't there. And so you can use this mechanism to supply an arbitrary function. So for instance, if this fun/odd, if this odd function didn't exist in the functional namespace, you could essentially build it yourself out of the raw material of the Clojure odd predicate this way. So this, again, these aren't completely analogous. This one is providing the value of applying odd to each element, whereas this one is extracting the indices for the elements that satisfy that predicate. But as we saw, I guess here, yeah, I'm sorry, I'm not explaining this as well as I'd like. I think my point still stands that for those cases where you need a function that's not predefined in the functional namespace, you can build your own. Although this is not an exact example of that. Okay. Thanks for the question. Okay, so we're going to move on to a slightly more elaborate example here. We're going to look at a a data set apparently from University of California that has some measurements of the sepal length of irises. Now, if you're like me and you don't know what a sepal is, it's apparently the part of a flower that encases the petals. And I guess you can characterize maybe certain species of flowers based on the sepal length. We have this URL here that holds the data set. And we're going to take advantage of some other built-in Clojure functionality. This is a CSV parsing library. And as you can see, it's trivial to download that URL and parse it into a conventional Clojure data structure. As we can see, this is a Clojure sequence. And here we have the first two elements of that sequence, which, whoops, happen to be 5-element vectors. We're concerned with the first element in each vector here, which corresponds to the sepal length that we're going to extract. So we are going to take this raw data and turn it into a Clojure vector, and then we'll move into dtype territory. We will use the emap function to extract the first element from each of these subvectors. And since there are strings, we will be creating a buffer of objects. Strings obviously aren't Java primitives. And then we will continue chaining map over that to take those strings and run the parse float method to yield a single precision float. So now that we've processed it, we can see that we no longer have a Clojure sequence. We have as expected, we have a buffer. And you may have noticed that we have to deal with a little bit of the anomalies of floating point arithmetic. This first value, this first value, for example, 5.1 as a string is being parsed as 5.099999 as a single precision float. That's just the wonkiness of floating point arithmetic. But what we're trying to do here is to normalize this data so that rather than having values of 5 or 4.9 or 4.7, we're going to scale those so that the smallest value maps to 0 and the largest value maps to 1. So we can use another pair of built-in functions in the functional namespace, reduce min and reduce max, to easily extract the minimum and maximum values of our buffer, and then subtract the minimum from each of those, and divide the entire buffer element wise by the difference between the min and the max. So this should normalize our data, but we see there's a hidden pothole in here that we may not have anticipated. We can see that the stack tracer is complaining about a number format exception. As it turns out, we have trouble parsing one of those values because one of them is actually an empty string. So of course, it's not surprising that we have trouble parsing an empty string. What is maybe surprising though is that dtype doesn't have any trouble creating this buffer, and we don't have any trouble taking the first 5 elements. Again, this just is another example of the lazy and non-caching properties of the buffer, that simply creating the buffer does not force it to be realized in a concrete way. And even when we take the first 5 elements, those 5 elements are all fine. The offending one is further on in the buffer. This again demonstrates that simply creating the buffer does not force you to pay the penalty of using that memory or the computational resources to make it concrete. Well, let's clean this up. So what if we take that chain of processing, and for the moment we'll simply avoid parsing it. Let's see if we can determine where the bad data is. So now again we'll use this arg filter operator to find any elements that are equal to the empty string. And again, this yields the index. As we can see, turns out there's only one element at index 150. So that seems simple enough to maybe just remove that one. So we'll create a function called clean that takes a buffer and identifies all the indexes where our test is not true. In other words, those are the ones we want to allow through. And then we will use the indices of the good values to produce a new buffer. So if we insert this clean function into our chain now, prior to parsing the floats, then we can see that, okay, the set of indices that cause problems is now empty. We've eliminated the bad one. And now we can successfully do the normalization that we wanted to. And as we can see, as expected, now all our values are scaled to the range of 0 to 1. Another way of confirming that our results are good is we'll exercise another function called concat buffers, which this sum function wants to work with a single buffer. Concat buffers will allow us to take multiple buffers and turn them into a single one that sum can then process. So if we take our good data that we produced above, and we apply this greater than function to identify which elements are greater than 1. So if, again, we're trying to scale the sepal lengths to the interval 0 to 1. Anything above 1 would be a mistake, and anything less than 0 would be a mistake likewise. And we're essentially coercing these Boolean values into ints here. So false would be 0 and true would be 1. So that if we sum them up, if there's any bad values, we should get a non-zero result here. But as we can see, we get 0 because there are no elements that violate our expectations here. Any questions on this set of steps? Okay. We're going to move on to what I think is the final chunk of the workshop. This is a little bit higher level. We're going to explore some integration between, again, our low-level dtype-next library and the TechML dataset, which is built on top of that. So the steps we just took to can you combine? That's a good question. So with the built-in less than and greater than operators, obviously we can apply that to 2 or 3
maybe it is good to repeat the question.
Yeah, sorry. So both are asking, I think if we can, rather than having 2 separate calls to less than and greater than, if we can sort of integrate those into a single one. So clearly, in normal Clojure, we could sort of chain those together as a single predicate test. In this case, let's see. Yeah, sometimes it's a little bit difficult to locate the implementation of these things because I think in this case, this is a multi-method. So in isolation, that call just is applied to each element and produces a Boolean value. Let's see if that works. Unfortunately, it does not appear to. So what's the problem here? I guess it's not explicitly complaining about the arity.
So it looked like it was looking for a sequence, but got a long, right? Got a number. And usually,
right. That's a good point.
Usually these functions are kind of graceful and are happy to accept either a primitive value like a number or a sequence or a buffer. But in this case, somehow it wasn't ready for the situation, right?
Right. So we saw that earlier. You know, I think maybe a analogous example would be here. If we subtract B from A, then we get a buffer. But what if we then subtract 2 from that? That seems to work fine, right? So I think, Lothar, your expectation is certainly reasonable. It doesn't seem to be implemented that way, though. Yeah, so as Daniel pointed out, it looks like it's expecting a sequence. Presumably this one is the one it's complaining about. No, that's a good question, Lothar. I'll have to maybe follow up with Chris. Sorry, though, I think that's the best I can do at the moment. Thanks for asking. So the final section here will move up to a slightly higher level of abstraction. We're gonna pull in this Tech v3 data set namespace, which is the Tech ML dataset library that we're yeah, I think there's a little bit of a trade-off there, Daniel, that I'm probably more responsive to the Zoom chat and you're following the Zulip chat better than I am. But thanks for the questions. So we're going to incorporate this Tech ML dataset library, and it has some conveniences that are not present at the lower level. We had to explicitly pull in this CSV file and process it a little bit ourselves here. But in TechML dataset, there's a function that will take a URL and simply turn it into a data set. Unfortunately, it doesn't quite work out of the box. We can see here the URL, the file ends in a .data file type, and this dataset function doesn't quite know how to cope with that as is. So we have to tell it that it's a CSV file. And then now it's not only downloads it, but parses it for us. And there's only one other hidden gotcha here. As you can kind of see from that printout there, the top row is actually being viewed as a header line, as though those first values were column names. You can see they're above the dashed line in the table. So we want to tell TypeML dataset that we don't actually have column names, that first row is data. So we'll do one final invocation here. And now it's sort of just synthesized some arbitrary column names for us, but we don't lose the top row of data now. All right. So let's capture that as a variable. And now one of the convenience functions of TypeML dataset, we can examine the head of that data set. I guess looks like just the first 5 rows plus the column headers or something. So that looks like what we expect. And we can still interact with dtype-next here. In this case, we'll extract the column 0 values, which are the sepal link that we were looking at before. We'll extract that from the table into a dtype reader buffer as before. And of course, this is not normalized yet as we did before, but these are the float values. And just for curiosity's sake, notice that we're incorporating this as double precision floats. And we can see that the representation is a little bit closer to what we'd expect. So it's the first value, instead of being 5.0999, whatever, single precision float, it's actually close enough to 5.1, and that's how it's being printed here. So if we, again, save this as a data value, now we're back in dtype world. We can see what are the types of the elements in there. And so again, this is a, we've created a data set, which is a table of data. We've extracted one column and turned that into a buffer. So once again, this is a dtype object. It has the appearance of a Clojure vector, as we've seen before. Again, it's, however, a reified buffer protocol instance. But again, we can see that that's not what I expected. I have to figure that one out. Sorry. On the other hand, so Yanni's asking if the sepal, which is a reader, did not convert to float 64, which is again the double precision float. I probably should have mentioned that TypeML under the covers, I think, does some little bit of magic as far as determining types here. Even though we're not explicitly giving any type information in this line here, let's see if we can. Let me continue on here. I think we'll see an example of that. So here we have a buffer, and here we're extracting the first column of the data set. And unlike here, where we are turning it into a reader, we're going to use it directly here. So the column is just one column of the TechML dataset table. And we can see that its elements are double precision floats. And this is as we can see, it's a column object. But within the column, there's a method called data. We can dig into that. We see that deep inside the column is actually this dtype buffer object. So as we pointed out, TechML dataset is built on top of dtype, and so it gives us some conveniences in terms of thinking in terms of a table or columns. Under the covers, it's still creating those substructures out of dtype. Oh, I see what, okay, so Oliver and Yanni are, I think they're noticing this discrepancy here, that in this case, I'm explicitly giving the type information to the reader function, whereas here when I define sepal, I didn't. But as I pointed out, the TechML dataset does some analysis of that for us. So we can see here, simply extracting the column, as we saw, this does know that it's 64-bit floats, double precision. And so I think sepal effectively, since we're getting sepal out of the TechML data set structure, I think it already knows that it's float 64. So in short, I think this is essentially redundant here. This thing knows already what's in there is double precision floats. And one final example is that, again, keep in mind that, again, sepal is a dtype-next reader. Column is a TechML dataset type, but these functions in the functional namespace are happy to work with either. So we can do a scalar addition to a reader, or likewise add a scalar value to each element of this column. Because again, fundamentally, even though the column itself is a TechML dataset type, it is built on top of a dtype-next buffer. All right, so that's really the end of the structured part of the workshop. I will remind you again, I encourage you to consider some of the follow-up exercises that Ethan has suggested here, and in particular this link to the NumPy exercises. I think some of Ethan's examples were inspired by some of these here. Aside from that, does anyone have any questions or comments? Anything you'd like to see a little bit more detail on, or? So Lothar is asking if you ever actually use the low-level dtype-next functions. That's a good question, and you're reminding me of a point that I forgot to emphasize. As I said before, the dtype-next library is relatively low level. It's a layer that these other libraries are built on top of. So in many cases, if you're using TechML data sets or tablecloth, you might be more focused on the table of data set, and maybe not directly manipulating buffers yourself. However, one thing that is clearly true, though, is that this functional namespace is used extensively at the higher levels. So in TechML dataset or tablecloth, you would probably be using some of these fun namespace operators, even though you might not be using directly creating readers or things like that. So the functional namespace is something that more people will probably use hands-on. All right, I think Daniel's already posted the link to the GitHub repo, Ethan's workshop that you can clone and play with. If you're curious, this slide deck also, this link is here in the workshop repo. So if you want to take a look at that. Thanks again to Chris Nurnberger for creating the library, and thanks to Daniel and Ethan for your support. I have another question here, Oliver. Okay. So Oliver's asking if dtype functions can be combined into transducers. That's an interesting question, and I think this came up in one of the earlier workshops that Ethan was doing. There was a comparison of applying a rolling window across a set of data using dtype versus a more conventional transducer framework. I think if you look in Zulip, the stream for the November 18th dtype workshop, there's some more details there. I don't know if that directly answers your question, Oliver, but there's a good side-by-side comparison there.
Yeah, I guess it is at least partly an open question, right? Because these two concepts are just different, right? And transducers, they apply to more general situations, right? Like where we cannot know, for example, the size of our data, right? Where even the data might be arriving as an async stream of data. So transducers apply to those more general situations. And then there is a question, could we use them still in these situations where we do know the type, the primitive type and the size of data without losing performance, right? Compared to the raw dtype-next performance that for the more narrow case. And that is a little comparison that we tried, really didn't dive into it so much. And we saw that the dtype-next rolling window was faster than transducers-based rolling window. Probably that other one could be optimized a little bit, but it looks like there is a gap. There is a gap between that transducers code, which is more general, and the dtype-next code, which is optimized for this situation. And it is an open question, I think, still. Could we make those situations closer? So, for example, one thing we have been discussing recently was about boxing. That I think you mentioned the fact that when we hold a number in a Java object, it is less efficient than holding it as a primitive Java value. And in transducers, naturally, we are passing around objects as inputs to the functions. So in that sense, it might be a little more wasteful than what we can do in buffers here. And it is a question whether it could be optimized to not need to box, for example. And I think we don't know yet.
Daniel, there's one other thought that comes to mind, something that was mentioned at the beginning. This deals with contiguous blocks of memory. With transducers, there is no guarantee of any contiguous blocks of memory. So if there is any indexing functions, then those cannot be really directly be applied into transducers. If there are any optimizations based on indexing into memory that way.
Yeah, right. And that is even more dramatic, possibly. Yes. Yeah. And we do know, could we come up with some new abstraction, which is transducers-like, but could kind of maintain some of these properties?
Thanks for your input, Rohit, and thanks for your explanation, Daniel. Just as a sign of how accessible Chris Nurnberger is, he's active in the Zulip chat right now. He's responding to somebody's question. So he's still actively involved with this library and very supportive. So it's good to see.
More than that, I'm online and listening to you guys.
Right. Okay. Welcome, Chris.
Thank you.
We haven't met personally, but thanks for your work.
Thanks so much for presenting it. It's always fun to see. It's very interesting for me to see what the community's understood and what they've adopted and how much of my ideas have made it out and how much of them haven't. And it's really interesting to see people, another person's interpretation, and trying to teach a library that's this complex and different, I think is a lot. It's a lot to take on. So thank you very much.
All right. I think we're close to the end of our time. Daniel, do you want to?
Yeah, David, thank you so much for this talk. And yeah, in a moment, maybe it makes sense to conclude, and maybe you would like to say a little more just as conclusion of this session. And what I thought was that maybe after the session ends, we could think a little bit if we could think about future workshops on this topic and future parts of the story that people here may like to hear about. So maybe after we end the recording, we'll discuss that a little bit. Does anybody else wish to say or ask anything before we end this session?
I would actually like to add something about the transducers discussion, if that's okay.
Please.
I think you guys hit a lot of the bigger points on it for sure. Some of it is, there's always been a tension between kind of infinite sequence processing, which transducers would kind of fit into, where you'll have a potentially infinite sequence. You have no idea where the end is. And I want to have a simple function that I can apply the sequence to produce a new sequence or something like that. And batch style processing, where, you know, I have an array of things and I'm going to do something to it and produce a new array of things. It's kind of, there's, in computer science, there's always been a tension between those two styles of programming stuff. And I think that where I try to merge those two is to transduce over sequences of data sets, or I transduce over sequences of batches of data, because then you get the kind of infinite data processing capabilities of transducers, but you get a lot of the efficiency benefits of batching your data up into primitive arrays and things like that. So the merge point may not be so much in transducing a single scalar over sequences of scalars of doubles, but moreover transducing over sequences of data sets or sequences of dtype-next containers of some sort. And that's kind of the big difference, is moving from a world where you can't possibly count everything, which is a transducer world, to a world where things are countable, and you can do it as the previous person mentioned, you can do indexed based operations. So you can do arg filter, or you can do sort by index, and that's a very, very different paradigm in a lot of ways. So there is some difference, and they do merge in some levels, but this is like a really old tension in computer science and in general in data processing, and one that I used to get in really strong arguments about with my old boss years and years and years ago. So it's never going to go away.
Chris, is this fundamentally even like the difference between like SACs and DOM parsers and XML?
Oh, that's a really good question. I'm not sure that it's so much between SACs and DOM parsers, but you can go all the way down to the definition of computing. So a Lisp defines computing in a very abstract sense in general. Like you have, you don't really deal with memory locations in Lisp in a base sense, or like lambda calculus. To abstract it further than Lisp, let's talk about lambda calculus. That's one definition of computing. Sure. Compared to like a von Neumann based architecture, where in reality, the way your computer works, you only ever have an array. You only have an array of bytes. That's all your memory ever is. There is no such thing as a boxed object or a scalar or something like that. All you have is arrays. And so there's this tension between how we want to think about computing, which is really some outgrowth of lambda calculus, because it's very natural and it's very correct, and the hardware truth of the matter, which is you only ever have an array of data. And you kind of are merging those two worlds. And it's just interesting that we can only get so close to merging them, and there's always a tension there.
I didn't think that this discussion was going to get any deeper or more abstract, but you managed to do so, Chris.
Well, you can imagine writing this. I was kind of, I really felt strongly that this style of programming was important to have in Clojure because it allows you to do, you know, a lot of the algorithms I'm used to from high performance computing. But I know that I'm working against some of the simplifications that Rich has worked so hard to put into the language, where once you start needing a data type and a length in addition to your sequence, those are two different pieces of data that now dramatically can complicate lots of systems. And so Rich's fundamental precept of we can make computing simpler is very, very true, but we can't do that and still address efficiently areas of big data processing and high performance computing. We have to accept some level of more complexity to move into those areas effectively. Or we have to accept a much more powerful compiler, which is what Scala did. And we all saw the kind of outcome of that. Like your whole world is dependent on whatever compiler version whoever is using at the time. And that's that's horrible, in my opinion.
Fascinating.
Yeah, maybe a small comment about transducers, if I can. So yeah, there is this gap between batch processing and async processing, right? When synchronous processing and asynchronous processing of data. And this gap is sometimes difficult. It is sometimes something that requires actually writing code in different styles, different code bases to handle the same types of data in those two different situations, where in one case we have it in memory and in another case it is just gradually arriving in a stream, right? And transducers are an answer to this gap. And you know, I remember being in that situation in other languages and other technologies, and it was actually a very difficult problem to write software that can handle the two cases. And our transducers allow that. And yes, they are not as efficient as dtype-next in the batch case, but they work kind of efficiently. And then batching a little bit into contiguous arrays could be considered like making it a little bit more efficient in a sense. So that is one of the reasons I'm excited about transducers. We are now around the round hour. And I guess maybe there are a few short comments or questions before we end this. And if not, then maybe we will ask David to conclude.
Yeah, I'm not sure what you're asking for here, Daniel, but thanks
Yeah,
for
you could just say goodbye. And
thanks everyone for listening, and thanks for your participation, Chris. I look forward to hopefully collaborating with some of you. There's a lot of interesting stuff to be done.